Go ahead, Muntash.
Good, it's Miss Seema Biswas. Good evening, everyone. Myself, Seema Biswas. Today, I am going to present my work entitled Flavonoids as Potential Therapeutics for Parkinson's disease. So, we all know that Parkinson's disease is one of the slowly progressive chronic neurological age-related disorder that affects a small area of the nerve cell located into the midbrain called substantia nigra. So these cells are normally produce a chemical messenger called dopamine. Many of the symptoms of Parkinson's disease are arise due to the loss of these neurons. Decrease in the dopamine level can cause the abnormal brain activity leading to the impaired movement and other symptoms of Parkinson's disease. So Parkinson's disease are broadly categorized into two forms. One is sporadic form and other one is the familial form. The interaction between the gene susceptibility and environmental factor are responsible for the sporadic form of Parkinson's disease, and mutation in particular genes like PINK1, Parkin, DJ1 are responsible for the familial form of the Parkinson's disease. Mutation in Parkin protein is most common cause of the autosomal recessive juvenile Parkinson's disease. PINK1 along with the Parkin protein participated into the mitophagy pathway, which in this pathway they remove the damaged mitochondria from the brain cell. So what are the potential etiological factors which can lead to the Parkinson's disease? As I already mentioned, then genetic factor like PINK1 Parkin mutation can cause the Parkinson's disease. Along with this, pesticide exposure. So environmental factor like some pesticide exposure and mitochondrial dysfunction, epigenetic modification like DNA methylation, changes in histone and oxidative stress can give rise to the Parkinson's disease. So mutation in this genes Parkin PINK1 and I also mentioned that the PINK1 and Parkin is participated into the mitophagy pathway. So mutation in this two protein can hamper the mitophagy pathway, which can lead to the ROS generation, and decrease the dopamine level can also cause the reactive oxygen species generation and misfolded protein aggregation into the brain cell. So when the misfolded protein get aggregated into the brain cell, then it forms the Lewy body and cause the neurodegeneration. Several dopamine antagonists are present, which are available to treat Parkinson's disease, but they have severe side effects. So in our work, we want to identify some beneficial flavonoids molecule that can be used in place of this chemically synthesis drug molecule to reduce the risk of the Parkinson's disease, and want to check how the flavonoid molecule can reduce the effect of the Parkinson's disease. From the literature, we know that the flavonoids molecule have the neuroprotectant ability, and they influence the neural cells, and also they decrease the reactive oxygen species. So our aim is to identify beneficial flavonoids molecule which can treat the Parkinson's disease caused by the PINK1 and Parkin mutation. For this work, we have retrieved the Parkin protein structure from the protein data bank, and we model the Parkin structure because there are some missing residue in it, and then check their quality. And we also select 60 flavonoids molecule from the literature, and also retrieve them from the PubChem data bank and optimize them, and check the flavonoids admit property, because admit property and Lipinski filter is a parameter which is used to identify a potential drug candidate. And then we further predict the active site of the Parkin protein, and then prepare the protein and ligand molecule, which are the flavonoids molecule, and finally dock them to the Parkin protein. Then we by using the autodock tool and find the binding free energy, and then we perform structure-based quantitative structured activity relationship to check how the admits properties, that is physicochemical properties of the ligands, are related to the binding free energy. So For this, we first divided out flavonoids molecule based on their backbone structure. So first group is the anthocyanin, and we have observed that the hydroxyl and methoxy group in the 4 prime, 3 prime, 5 prime, and 7 and 6 position can affect the binding free energy. Cyanidine is the base binder in this group. The binding free energy is minus 8.79 kcal per mole. And addition of the methoxy group in the B chain can lower the binding free energy. However, if the methoxy group is present into the 6 prime position, in case of pitidine, it lowers the binding free energy more. So when we compare the flavone molecule, we have observed that the presence and absence of methoxy and hydroxy group in A ring and B ring can significantly change the binding free energy. Butene is the base binder in this group, and if the branching side chain is present, then it can lower the binding free energy, which is in case of hesperidine and naringine. When we compare the flavone molecule, we have seen that 6-hydroxyflavone is the base binder in this group, and followed by the ugonine, bicalene, 7,8-dihydroxyflavone. Presence or absence of the hydroxy and methoxy group in the B ring can significantly increase the binding free energy. However, if the methoxy group is present and hydroxy group is present in the B ring, then it can lower the binding free energy, which can be observed in this slide. When you compare the flavonol molecule, the azathioprine is the base binder, and azathioprine is the base binder among all the group of flavonoids molecule. So here we can see that the branching side chains here also can reduce the binding free energy. In case of lutein, we can observe that if the methoxy group is present in the 3 prime position, then it can also lower the binding free energy. However, this position is very important. When we compare the ranitidine and rhamnocin, we have seen that the presence of hydroxyl group in this position lower the binding free energy. When we compare the isoflavonoid molecule, that is the base binder in this group, and we have observed that presence of the methoxy group in 5 prime position can lower the binding free energy, and also branching side chains can lower the binding free energy. When I compare the chalcones, we have seen that the epicatechin and catechin is the similar have the similar structure, and due to the similar structure, their binding free energy is also similar. When you compare the epicatechin and epicallocatechin 3 gallate, we have seen that branching side chains can lower the binding free energy. Fluoridine is the base binder in this group. When we compare the flavonol molecule, we have seen that garbanzol is the base binder in this group, and more present of the hydroxyl group can lower the binding free energy. After that, we want to check how the binding free energy is related to the pharmacokinetics property of the ligands. So we have picked the most commonly used drug ligands properties like X log P3 value, topological polar surface area values, water solubility values, blood brain barrier values, and molecular weight. And we plotted them individually and we built a linear regression model to check how the binding free energy is related to this drug likeness properties. And we also analyze their coefficient of determination, that is R-squared value. And we have seen that the molecular weight show a relationship with the binding free energy. We have already know that the R-squared, if the R-squared value is greater than 0.5, then we can say they are related. So here the molecular weight.
Sorry, Seema, you need to wind it up. Please conclude.
Ma'am, I will take one moment.
Yes.
So if the R-squared value is greater than 0.5, then we have said that it are related. So here the molecular weight shows that the R-squared value is 0.674. So to check the avoid the biasness, we divided the flavonoids molecule into the three set. We keep the 40 flavonoids molecule in training set and 20 flavonoids molecule in test set, and we individually plotted them. We randomly picked the samples and individually plotted them, and also calculate their R-square values. And we have between the three sets, we have seen that the R-square value is almost same, and there is some negligible differences. Using this data, we also predict the molecular weight of the flavonoids molecule, and also we plotted them against the binding free energy. And we have seen that
Miss Seema, please conclude. Please conclude. Give a conclusive statement. Yes.
I will take 30 seconds. So we have seen that there is a relationship between the molecular weight and the predicted R-square value. R-square value. So at a conclusion, we can say that if we know the binding free energy, we can predict by using this model, we can predict their molecular weight, or if we can know the molecular weight, we can predict their binding free energy using this model. And after this study, we can say that azolitine will bind more potently to the Parkin protein, and it can be used as a potential drug after some wet lab experiments. And in future, we want to design some small products that can target the damaged pink-1 protein to enhance the damage sensing ability. So lastly, I want to thank Professor Anshuman Bakshi for his guidance, deeply funded bioinformatics infrastructure facility, and the Longevity Asia for giving me the opportunity to present here. And lastly, thank you everyone for your time. And
thank you. Thank you, Seema. So we have seen your ambition of highlighting the potential therapeutic strategies of flavonoids. In consideration to the time, we have to stop you. Thank you. So we encourage the audience and we encourage everyone, whoever is interested, to put your questions in the chat box, and you can see the chat box to answer them by the end of the technical questions. Thank you. Okay.